Sorry. Now we're recording. Okay, so hi everyone. My name is Alon, and let's talk about pausing and resuming WebAssembly with Asyncify. So what am I going to do here? I'm going to give an overview about what problems Asyncify aims to solve, how you would use it. So I'll show a few concrete examples of how you do it. I'll explain a bit about how it works, so the underlying details, even though you don't need to understand all the details. And I'll end with a demo of something that I'm pretty sure you didn't know was possible in Wasm. So the problem here is that web APIs are asynchronous. Now, of course, this is not an actual problem for the web. This is great for the web, but it's a problem for WebAssembly sometimes if you compile a code that depends on that. So the code here has, can you see that pointer? So this is a fetch, the most archetypical web API. It returns a promise that is the console.log will happen at some point in the future when the fetch data actually arrives. But if you have this code that's compiled into Wasm, so get data and then use data, if get data calls that JavaScript, it'll return immediately before the promise happens. And if you call use data, the data is not there yet. So that's not good. So a great idea is simply rewrite everything async. Pass around a callback, just refactor your entire code base. Wonderful idea, great. Maybe not that great an idea because you might have a very large code base. It might be very hard to refactor it. And it might be someone else's code. It might be a library that you're porting. So in practice, this is just not great. Another option, interpreters are very helpful in this because you can pause and resume execution whenever you want. So you can pause, wait for some async event, and then resume later. So you can run an interpreter in Wasm. You can just compile one. It's easy, but it's going to be pretty slow, obviously. Historically, though, this is actually one of the solutions we had. So the interpreter option in Emscripten does exactly this. It compiles a little interpreter to asm.js or to Wasm. It runs about 10 to 20 times slower than full speed. But it works. So it's interesting that even though it's massively slow, it had a bunch of users that were very happy because it let them run code. So that kind of shows the importance of a solution. Finally, another option is to wait, not just to wait for a promise, but to literally wait for Wasm to support this natively, which we hope it will someday with something like stack switching or some other native support. When that happens, this will be the preferred solution, obviously, because it'll be fast and optimal. But we don't have this yet. Okay, so what we want is something that's easy to use. We don't want to refactor a massive code base. We want something reasonably fast. Some amount of overhead is expected, but we don't want a massive slowdown. And we want something that works now. So I'm up here talking, so obviously I have something that does this. That something is Asyncify. And the big picture is Asyncify provides low-level support for pausing and resuming Wasm in an efficient way. The basic idea is it instruments the code. So if you start with some Wasm, you run Asyncify on it, and you get another Wasm. And that Wasm has the ability to be paused and resumed at any point of interest. Practically speaking, Asyncify is a Binaryen pass. Binaryen is a toolkit for WebAssembly. It lets you do things like optimize the Wasm. So it has a command line tool, wasm opt, and you can just run wasm opt on any Wasm file, tell it --asyncify, and it'll output a Wasm file that has this support. We'll talk a bit more about the optimizations here later too. And you can also do this not just on the command line, but in JavaScript. There's Binaryen.js on npm, so you can just grab that and run the Asyncify pass, and that's it. Asyncify provides a very simple API, just 4 functions. So a function to start unwinding the call stack, to stop, and to start rewinding the call stack, and to stop. So that's all it does. You can sort of unwind the call stack and rewind it. And when you rewind, you'll be exactly where you were before, as if you never left. That's the whole idea. OK, so let's see how we would actually do this in practice. So this is an example of some Wasm code that's going to call JavaScript, and JavaScript will sleep. So this Wasm imports 3 functions: before, sleep, and after. And then the main function calls before, then it calls sleep. It asks to sleep for a second. We want it to actually pause during this time, and then it'll call after. So imagine that we've instantiated that Wasm module, and we have the export, so we simply call the exports, of course. We call main. Main, as we saw, will call sleep. After it calls sleep, the stack will unwind, so it'll unwind all the way out to right after the call to main, which is right here, right after that call. At that point, we just call Asyncify stop unwind to tell it that the unwinding has reached the end and we can stop. And that's all we need to do here. So when we called sleep, it set up some sort of asynchronous event for the future. It set up whatever we need to restart ourselves. But in terms of the code we write after calling main, all we need to do is to stop the unwind and then wait for the async event, which will happen. So the interesting thing is what happens in that sleep function. So before I show you the code for sleep, I want to explain a bit about a weird thing that's a bit tricky to follow, that sleep is actually called twice. So in this graph, you can sort of imagine the x-axis is time, and the y-axis is vaguely the call stack. So if you imagine that we run code normally for a while, then we call a function, so we rise in the call stack, then we run some more, and then we call sleep. Sleep will do something, and then it'll unwind the call stack all the way out. Once we're all the way out, we're outside of the Wasm. No Wasm is running. We can then pause, wait for async stuff to happen, however long we need to wait. We'll then rewind the call stack to exactly where we were before, all the way back up. And where we were before is where we started the sleep, operation, which is in the sleep function. So we actually call sleep a second time. Sleep then returns after finishing whatever it needs to do, and then we carry on normally. So kind of what we expect to happen here is for sleep to be called twice, which maybe is a little counterintuitive. Okay, so here's the actual code for sleep, just a little JavaScript. It's pretty simple. So as I said, sleep will be called twice. So the natural way to think about that is kind of some global state. Are we already sleeping? If we're not sleeping, if this is the first time that we're called, then we can do this set timeout, and for some amount of milliseconds in the future. And when the timeout fires, when the appropriate time period has passed, we call Asyncify start rewind. That tells the code to be ready to rewind itself, and then we actually call main. The reason we need to call main is Asyncify modified the Wasm, but it does nothing on the JavaScript side. So we need to actually re-enter the Wasm in order for anything to happen. Okay, so we do the set timeout, and then we simply call start unwind, and then the unwinding will happen, and we'll wait for the asynchronous event. And that's it. On the other hand, if we're already sleeping, if this is the second time we're called, we simply call Asyncify stop rewind because we were just rewound to here. And we flip the state, and that's it. So it's pretty simple. To do this in JavaScript, you just set up some JavaScript runtime code like we saw. You run Asyncify on the Wasm, and that's it. You basically have Wasm that can pause and resume, and you didn't need to refactor any of your source code at all. Okay, it's also possible to do this in pure WebAssembly. So it's kind of similar. You call the Asyncify API just like you called it from JavaScript, but now we're doing it from Wasm. So if we maybe call this the lower runtime because it's kind of underneath main, it's what calls main. So this is some Wasm code that calls main. Just like before with JavaScript, after main calls sleep, we'll unwind to right after the call to main, at which point we call Asyncify stop unwind, and that's it. And that's great, except that we did this in Wasm. If we instrument this code itself, this lower runtime function, we'll just unwind all the way to the outside, and there's nothing outside of the Wasm. All we have is the Wasm. So this won't quite work as it is. So Asyncify is a simple rule. It will not instrument a function that contains an Asyncify API call. So just like the function on the previous slide, or this function sleep. So this is actually the sleep function in Wasm. Just like in JavaScript, it'll check, are we already sleeping? And if we're not, then it'll start the unwind, et cetera. So when Asyncify sees these API calls, it just doesn't instrument the function. It assumes that's your special runtime code. And this generally does exactly what you want, except that you need to maybe be careful of inlining. If you're in a language that might inline code into your runtime, that could be a little weird. So you might need to add no inline or something. But aside from that, using Asyncify in Wasm is basically the same as JavaScript, very simple. You define imports to the Asyncify API, so it's the Asyncify module and then the function name. You set up your runtime code. You run Asyncify in the Wasm, and you're done. OK, so we saw two examples of how to do this at the very lowest level, by which I mean we actually wrote our own runtime code. But you can also do it in a higher level language like C. So Scripting has built-in integration for Asyncify. Basically, any of the Asyncify-powered APIs like Script and Sleep, you just call them. It's also easy to add your own. We'll see in a few slides. And you just build with the Asyncify flag -s Asyncify. And that's it. You don't need to write any runtime code. It just works. So this is a complete example that I'll run in a second, assuming I have a network connection. So before I run it, just to tell you what it's going to do. So the main function here has an EMASM. EMASM is a convenient way to write some JavaScript inside C and just call it. So this JavaScript is going to do a set interval 1, which means it'll run an event it'll try at least to run it once every millisecond. It's going to change the background color in some way. So the whole point is just to show that events are happening. So you should see the background color change. And we're going to do that while we run an infinite loop, which you can see over here. Just while 1, this loop will never exit. The loop will try to print something and to sleep for a second. So if we compile this naively, it wouldn't work. The infinite loop would never exit. The whole page would just hang. You wouldn't see the printing, and you certainly wouldn't see the background color change. With Asyncify, though, the call to sleep actually turns into an exit from the loop, a return to the browser's event loop. The browser can handle events, and then it'll return to the loop as if you never left. Now, hopefully, we'll see this work. So you can see the color change, although the frame rate isn't great here. And you can see the printing. It prints once per second there. Anyway, so it works. So that example was a bit simplistic, just to show that it can work at all. But this is actually not a rare pattern. That sort of while 1 loop is pretty common in things like game engines. They're just written that way. Typically, they have a main loop like that. Typically, you can also refactor it pretty easily because there's just one. But often there's a bit more code like that in the code base. For example, Doom 3 was ported several months back. And it turns out that a bunch of their cool effects, like the terminals and other things, are actually written using this synchronous code. So the dev just basically used Asyncify in the code base, and those events now work in that port. OK, last example. So this goes all the way back to the first slide where I showed you a promise, a fetch that we want to wait for. So in this slide, I basically show you how to block on any asynchronous event in JavaScript from C. So we use em.js here. Em.js is a convenient way to define a function in C whose body is in JavaScript. So doFetch will do a fetch, obviously. And we call asyncify.handleSleep. All this does is handle the sort of to-call thing. So we call handleSleep, and it handles all the check if we're sleeping already for us. It gives us a function wakeUp. We simply call wakeUp at the right time, and execution continues. So we do the fetch, and then we wait on the promise. When it happens, we do something with the code, typically with the data, typically, but then we call wakeUp, And in the main function, we print out before, then we call doFetch. Only after the fetch gets us the data do we get to the next line and print after. So in this way, you can basically connect to any asynchronous API in JavaScript and conveniently wait for it to resolve. Okay, so a few examples. I've already mentioned Doom 3 that uses Asyncify for the effects. The Julia programming language uses Asyncify in their web port to implement coroutines. You need to kind of pause and resume. And the DOSBox emulator, which is cool if you like to play old games from the 90s. It has a bunch of event handling code that's very synchronous and very hard to untangle, so they just use Asyncify on it and it runs. Okay, so I've showed you that this works, but you're probably thinking, well, this can't be fast. How does this even work? And it's probably extremely, extremely slow. Well, let's see a bit more about how it actually works. So after running Asyncify on a binary, we get a bunch of changes. So one of them is this. So if we had this call beforehand, after every call, we need to check if we're starting to unwind the call stack. If we are, then we need to do something. In particular, we need to save the locals and exit the function. And we keep doing that until we unwind the whole call stack. So we need to check after each call. You'll have something like this. Get the global state, check if we're doing an unwind. If so, do a break to the proper place, which will handle things. If we're rewinding code, we need to skip code that we've already executed. So imagine we have a store, and if we did a sleep sometime after the store, we need to get back to that place, but we don't want to re-execute the store. We've already done it. So we'll have something like an if, are we doing a resume? If we're doing a rewind, don't run the code. But if we're running normally, do run the code. So these ifs are going to be around basically any code that does something. Finally, near the top of every function, you'll have something that checks if we're rewinding the call stack. If we are, we need to restore the local state. So you'll have something like check if the state is doing a rewind. If so, have a bunch of loads. Each load goes into a local, so basically load the locals back. So that's a lot of changes. All the calls, all the instruction now have ifs around them, so that seems pretty slow. But we work very hard to get rid of this overhead. I'll show you numbers in a few slides. But first, the idea of how we optimize this. One thing is we do an procedural analysis to figure out what functions even need the instrumentation. So if the cursor's red and this is red, so you can't really see it. But anyway, if this function calls this one, which calls sleep, we're forced to instrument these three. But if these two functions never call sleep, we'll never need any instrumentation in them, and we just leave them alone and they run at full speed. We also optimize inside each function. So any code that doesn't unwind can run at full speed. We don't touch it. So even if you have something like a loop, and the loop might have a bunch of stores, it can even have a call to code that we know can't unwind. So this whole loop will run at full speed because we know it's safe to not modify it. And when we check whether we need to skip the code when doing a resume operation, we have a single check for a whole clump of code like this. So we don't do it around every single store or every single call, but around entire batches. Another thing we do is we integrate with the Binaryen optimizer. So Binaryen has an optimizer that's general purpose. It just gets rid of unneeded locals. It finds various patterns to optimize. So Asyncify just instruments the Wasm and then runs the optimizer, and it typically finds many, many opportunities to shrink the code. But overall, the key sort of insight or the key idea in keeping things fast is Asyncify's instrumentation doesn't create any new functions. There are other approaches in this space that do create new functions, and they have benefits and detriments. But I think in Wasm, the Asyncify way works pretty well. So we don't create new functions. We don't even change control flow in any significant way. An alternative approach would be to turn every function into a switch in a loop, and then it's easy to jump back to the right place in the switch in a single operation. Good for resuming, but has other downsides. All Asyncify does is it adds those ifs to skip code when resuming. So there's also the saving and loading of the locals, but that's actually pretty minor for perf. The thing that actually matters are those ifs. And those ifs are pretty fast, actually, so don't try to read this code here. But you can imagine that you have a potential skip from here to here, potential skip here, and so forth. If sleeping is rare, and it's probably rare if you're using sleep for something like a fetch, so you're not doing 1,000 of these a second. So these ifs are all going to be false. That is, we're not going to skip. We're just going to keep running normally. On a modern CPU, this is going to be very, very fast. So in practice, the overhead of these ifs is very, very low. And that's the key idea. By the way, this picture is also kind of a good way to think about how the resume operation works. So you can imagine if we skip over some code, we get to here, skip over to here, and then imagine this is the call where we started the sleep operation. So we enter that, we stop the sleep, and then we keep running code later. So you can kind of imagine that you just keep skipping till you get to the right place, and then carry on. Okay, so that's great, but of course, numbers are what really matters. So this slide has a bunch of benchmarks. These are CPU-intensive benchmarks. These benchmarks do not actually sleep. These are just standard benchmarks, but we'll run the instrumentation on them to see the overhead. So each benchmark has 4 measurements and 4 thin bars, which hopefully you can see or at least get the big picture of. The first measurement is without running Asyncify at all. The second is sort of the worst case. We assume every import and every indirect call may sleep. This is realistic in the sense that when we optimize the Wasm, we don't know what those imports will be. And it's very hard to tell where an indirect call will go. So we pessimistically have to assume that we need to instrument them because they might sleep. So even though these benchmarks don't sleep, it looks as though they do when we instrument them. So you can see we about get to the 50% mark. That is, Asyncify adds something like 50% overhead. In the third measurement, though, we give it a list of the sleeping imports. So we tell it these imports can sleep and these can't. Again, in these benchmarks, nothing sleeps, so we just tell it ignore the imports. And that helps in a bunch of benchmarks. Finally, if we also tell it can ignore indirect calls, you see the overhead goes basically back down to the starting point. So it's kind of like there's no overhead where it's not actually needed, where we can prove we don't need to instrument code, we just don't create it, or we optimize it out. But you do need to tell it what it can optimize out. So you need to tell it which imports matter. You need to tell it whether indirect calls matter, and in some code bases they simply do, so you have to keep them around. And we also have a whitelist, blacklist mechanism, so if you have to do some sort of, if you must get the absolute maximum speed, you can actually tell it ignore these functions or only instrument these functions, etc. That takes a bit of manual work. All the rest of Asyncify is automated. This, if you really must, then you can do some work to make it better, but it does take some effort. Okay, getting back to that worst case overhead. So we saw that 50% number. So if any import and every indirect call can sleep, we generally add something like 50% overhead. So that's not great. Obviously, you don't want this. Nobody wants 1%, much less 50% overhead, but it's not terrible. Many code bases run pretty decently at 50% slower. Again, from the beginning, I told you we used to have an option that runs 10 to 20 times slower, and people were pretty happy with it. But anyway, again, this is not great. You can use the whitelist, blacklist mechanism if you really need more speed than that 50%. Okay, a few final words on optimization. So as I mentioned, it's important to optimize when using Asyncify. It adds a lot of instrumentation. So unless you're debugging, always optimize. There are some numbers here. So this is a benchmark. This is The benchmark with Asyncify on it, it's much bigger, it's much slower, it's terrible. If you also optimize, it gets to that 50% area. So it's important to remember to optimize. Also, kind of as a side note, it's important to optimize in general. Whenever I get a link to some new website using Wasm, I download the Wasm and I run Wasm opt on it. Half the time, it gets like 20, 30% smaller. So just like JPEGs or JavaScript, you can minify your Wasm. We have the tools. Please use them. OK, so I'm almost at the end. I want to talk a bit more about the Asyncify API, and then I'll show you that demo that I was talking about. So I've slightly simplified the API. The start unwind and start rewind commands take a parameter. They take a pointer to a buffer. The buffer is just some memory that we use because, as I said, we need to read and write the locals. So we use that memory for that. We also need to remember which calls to return to. So we have some information that we write out and then we use to resume. You don't need to think about the contents of that buffer, but you do need to allocate it. And this is kind of similar to the SetJump JumpOff, if you're familiar. So SetJump in C is a function that you call. It saves the program state. Later, you call longjump. Longjump returns back to the SetJump as if by magic, basically restoring the program state, including where we were. And that's basically a way to kind of jump from one place to another. And it uses this JumpOff, which typically contains the stack, the registers, some information, which again, just like with Asyncify, you don't need to think about it, but you do need to allocate it and pass it around. So speaking of SetJump, does it actually work in Wasm? So yes and no. In Mscripten, it's worked for a very, very long time. So you can compile code to Wasm and JS, and it'll run on the web. It'll run in Node.js. It'll run in Wasm or anything that supports that. It depends on JavaScript or on support for the invoke, dyn-call special imports. So it doesn't work everywhere. It will eventually work everywhere because we're going to add exceptions to Wasm. So Wasm will natively be able to kind of unwind the call stack, which is really all SetJump needs. But we don't have that yet. So right now, SetJump does not work in either pure MVP 1.0 Wasm or in WASI. In fact, the WASI SDK doesn't have SetJump.h because it's just too early. It's not there yet. But maybe we could implement this in Wasm. So Asyncify, after all, lets us pause and resume. So you go from one place to another. And longjump kind of also moves from one place to another, too. So if I'm talking about it, obviously, I'm going to show you a demo of this. So this is the program I'm going to compile and run. I just want to quickly go over it before I run it so you know what to expect. This is basically the hello world of SetJump. It's pretty simple. So there's an inner function that just calls longjump for us. The main function will print start. The expected output is over here in the lower right. So it'll print out start. Then we call SetJump. The weird thing with SetJump is it is reached twice. So the first time we just call it, it returns 0. So we print call inner and we call inner. Inner calls longjump. Longjump jumps right back to the SetJump. It returns the new value here, which is 1. And then we get to the else. We print back from longjump and end. So this is the expected output if you just compile this with GCC or Clang natively. This is how SetJump works. OK, so let me show you how that runs in Wasm. And I'm going to switch off this microphone. Can you hear me? Hopefully, I'll manage to type while I'm doing this. So this is not convenient. So I'm going to run these commands. I just have them written out here, so it's easier to read before I write them in a terminal. Without getting into all the flags, which don't really matter, I'm going to basically run clang to compile jump.c to jump.o, Wasm LD to compile jump.o to jump.wasm, Wasm opt to go from jump.wasm to a jump with Asyncify jump async.wasm, and then I'll just run that in a VM that supports WASI, because I'll be using WASI for printing. So that's it. Let me actually do that. Okay, so first, maybe I can, this is really not convenient. First, let me just show you jump.c. No, there's no good way to do it. Thanks, though. I can manage. I mean, thankfully, I just have these, and I just need to press up and then enter. So I don't need to actually type, but whatever. But thank you. So this is the function. This is the code that I showed you before. It's slightly modified in that I added no inline, for example, because of the inlining issue that I mentioned to you before. But otherwise, this is the same code from earlier. So we'll just print call long jump in this inner function and call long jump. The main program is renamed to user program just because this is WASI. So the start is a bit different, but whatever. But otherwise, this is the same. We'll print start. We'll call SetJump, et cetera, et cetera. So it's the same code, just slightly modified. And this file also contains the runtime, which, if I have time, I might go over a bit. But otherwise, let me just run clang. Can't quite see that at the bottom of the screen there, but trust me. I guess you'll see it when it scrolls up. Wasm MLD and Wasm opt. Now I can actually look at the files. So you can actually see here that jump.wasm, the original file, is about 6K. The async one is actually smaller, which is kind of weird because we've added instrumentation to it. The reason is we've also optimized while doing it. So the optimizer found enough opportunities to make up for the extra overhead. But in general, of course, it would be bigger, not smaller. And that's it. Now we can run it in Wasmer, for example. And this is literally the exact output you'd get from running it natively. And there's a question in the back. Let me just run one more command. And you can run it in Wasm time too. Same thing. It's all the same. Yes. Oh, thank you. That was a thumbs up, not a question. Perfect. It's the best kind of question. Yeah, so you can do SetJump in pure Wasm, pure MVP Wasm, without any fancy JavaScript or anything. So time-wise, so I don't have a lot more time. Let me just quickly explain the idea behind how this works and maybe not get into the code much. So the idea is we implement a SetJump as an unwind from one place and a rewind to another. Now, normally long jump goes directly from one place to another. We can't do that here. We'll unwind all the way out and rewind all the way in to a different place. Or in slightly more detail, you can imagine we'll run to the SetJump. When we get to the SetJump, we will unwind and immediately rewind the SetJump. The only reason we do this is to be able to rewind the SetJump again later. We then run to the long jump. We unwind the long jump. We will never rewind that buffer. We just unwind it. And then we rewind the SetJump buffer, and we're back at the SetJump, which is where we want it to be, except the runtime also gave us the new value, the return value from the long jump, and we can carry on executing. And that's it. The rest, there's a bunch of details to implement, but that's it. I think I'll skip getting into more of the code and leave time for questions if there are any. Thank you.
Any questions? Got the mic? Yo.